All right, welcome everyone. As a reminder, our exam is coming up. So on Monday, we'll be doing a review session, and that will be my answering your questions about the review problems. So those are available on Canvas under Practice Exam 1. So there's a practice exam quiz on Canvas. There's a take-home practice exam with some examples of questions I might ask you about in R. And then there's a sheet of extra practice problems that are similar to the ones on the in-class portion, so the Canvas quiz, that are just extra. So I had more practice problems than would fit on one practice exam, so those are available here. So I highly recommend that you try at least some of those between now and class on Monday so that you know which questions you want to ask about during the review session on Monday. And also be working on what you want on your 3" by 5" note card, both sides. Are there questions about the logistics for the exam? Folks online, any questions? All right. So today's material is on the binomial distribution. So this is material that will not be on exam 1. This will be on exam 2. And this will be included on homework 4, which is available now. So based on what we're doing in class today, I recommend trying problems 3.37, 3.39, and 5-36. All right, so the binomial distribution is a model for random processes that involve binary outcomes. So outcomes that can either be yes or no. They have 2 possible options. Oops. And they describe the probability of having capital Y, so our random variable Y, is the number of yes results in a sample of size little n if the probability of success on any one observation stays the same. So our probability of success is always P, and the trials are independent. So a good way to think about the binomial distribution is that it models things that could be simulated by flipping a fixed number of possibly biased coins. So the coins are all independent. We know in advance that we're going to flip little n of them and then count up the number of heads. If we can simulate the situation that way, then we can use the binomial distribution to compute probabilities of the numbers of heads. All right, so let's take a minute to think about what sort of scenarios we can apply the binomial distribution to. So for number 1, take a minute to read through this and think about whether this is a binomial experiment. So in other words, whether the binomial distribution could be used in this scenario. All right, let's see, thumbs up if you say yes, we could use the binomial distribution. Thumbs down if you say no. And folks online, you can use the agree and disagree options in your status bar down at the bottom. All right, so I'm seeing thumbs up. Yeah, I would agree. Vivian, why did you say thumbs up?
Because each stroke is independent.
Yeah, that's what this missing a free throw doesn't make her nervous business is about. So that's saying that the results of one free throw doesn't affect her probability of success on the next free throw. All right, how about this one? Take a moment to think about that. All right, let's see. Thumbs up for yes, it's binomial. Thumbs down for no, it's not. See, thumbs down, thumbs up. Some people without thumbs. Niall, why do you say thumbs down?
The probability of drawing these changes as the experiment goes on.
Yeah, because we're drawing without replacement, we're taking the cards out and not putting them back. As we draw more cards out, the probability of getting an ace is going to change depending on whether we got an ace the last time or not. So here, the probability is changing and the results on different trials are dependent. So we would not want to use a binomial distribution for this. Instead, we want to use a hypergeometric distribution, which we'll talk about next week. How about this one? All right, let's see. Thumbs up for yes, it's binomial. Thumbs down for no, it's not. Okay, so I see thumbs up, thumbs sideways. Kyle, why did you say thumbs up?
Because the chance of having type O negative blood doesn't change per person based off of a different person's results.
Okay.
That makes sense.
Niall, why did you say thumbs sideways?
Because we know everyone in the U.S. Or there's 7% probability that everyone in the U.S. has high O negative blood, but we don't know the probability of these specific 10 people.
Okay, so a simple random sample means that every set of 10 people is equally likely. So we can think of this 7% as referring to the probability of any one person within the sample. So Kyle is correct. We have this 7%, so that's our probability that any one person has type O negative blood. The reason you might possibly think, I'm not sure, maybe thumbs sideways to thumbs down, would be technically, this is sort of the same situation as in number 2, right? We're sampling people without replacement. We're probably not going to test the same person's blood twice in a row. So technically, once we've sampled one person, now there's 7% of the US minus one person left to have O negative blood. So in a very technical sense, people here, if we're doing our sampling without replacement, are technically dependent. But if the sample size is small relative to the size of the population we're sampling from, then the probability changes by such a tiny amount that we can effectively treat the people as being independent. So here, I probably would use the binomial distribution in this case, But if we were sampling 10 people from a smaller population, such as the population of math majors at UWEC, then I might not want to use a binomial distribution. Then I might use a hypergeometric distribution instead. Questions about this? Folks online, any questions? Realized I forgot to test out. Yes, I can hear you. All right. So for computing probabilities from the binomial distribution, here's our formula for finding the probability that our random variable y equals some specific value little y. So take a moment to write that down, and then we'll talk about it. All right. So here, n is the number of trials, or the sample size. Little y is the number of yes results whose probability we're interested in finding. P is the probability of getting a yes result on a random trial. So P has to be between 0 and 1. And Q equals 1 minus P. So that's the probability of a no result. So let's think about why this formula makes sense. We're doing n trials, say flipping n coins, and we want to know the probability that y of them are heads. So this p to the y is taking the probability of, say, heads on any one trial and multiplying it by itself y times. So that's giving us the probability that y of the trials are yeses, treating those as independent, right? Because if they're independent, then we can multiply their probabilities to get the probability of the intersection, that all y of them were yeses. This q to the n minus y is the probability of a no being raised to the power of the number of no's, right? N minus y. So that's treating the trials as independent. We can multiply the probability of a no for trial number 1 times the probability of a no for trial number 2, dot, 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 to get the probability that all of those n minus y trials were no's. What is this n choose y doing out front, do you think?
Because the probability of yes can be anything.
What's that?
Because the probability of yes can be anything or anything.
Yeah, so this is accounting for the fact that we don't care about order. We only care about getting y yeses. We don't care if they're the first y or the last y or the ones in the middle or sprinkled however. So this is the same thing that we talked about with our inspector testing defective products example. If we say have n equal to 3, and we want the probability that y equals 2, there are 3 ways that we could get 2 yeses out of 3 trials. We could have yes, yes, no, yes, no, yes, no, yes, yes. And each of these has probability p squared times q. So the n choose y is the number of orderings of the yeses and the nos. So we say that the probability that y equals 3 is going to be 3 times p squared q, or more generally, n choose y times p squared q. Questions about this? All right.
Wait, I have a question.
Yes.
So how is n choose y in that situation equal to 3?
How is n choose y equal to 3?
Yeah.
So in this case, n choose y. Oops, sorry, stop sharing my screen again. Is 3 choose 2? Because we had n equal to 3 and little y. Oops, sorry. Y equal to 2. Little y is the value whose probability we're trying to find. So that's going to be the number of ways to choose 2 objects out of 3. So you can think of that as, in order to choose 2 objects to be yeses, you can choose 1 object to be a no. And there are 3 ways to do that. You could pick any of the 3 objects. And in the formula, that'd be 3 factorial over 2 factorial times 1 factorial. So 3 times 2 over 2 times 1 times 1. So the 2's end up canceling, and we're left with just 3.
Okay, that makes sense. It was just confusing because it said y equals 3.
Yeah, sorry about that. I'm going to increase the volume of my hair. All right. As a side note, what values of y is this formula valid for? Niall?
0 to 10.
Yeah, 0 to n. Integers from 0 to n. Because y needs to be the number of yes results. So if it's a number of results, then it needs to be an integer. We could have 0 yeses, or we could have up to all of the trials being yeses, but we couldn't have more than that. All right. To compute binomial probabilities on a calculator, if you have a TI-83 or TI-84, the way to do that is to press the second key and then the VARS key. And then select Binom PDF. So the P in PDF stands for probability distribution function. You can think of that as representing a particular value. We're looking for the probability that our random variable x or y equals a specific number. And then the order of the arguments is n, p, and then x. So our sample size, comma, the probability of a success on any one trial, and then the desired number of successes that we want to find the probability of. So for example, if we want the probability of getting exactly 3 heads when you toss 4 fair coins, we could use binom PDF 4 for the number of coins, comma 0.5, the probability of heads, comma 3. Similarly, if we want to compute the probability of x being less than or equal to x, you can press second and then vars, but then choose binom CDF. So the C in CDF stands for cumulative distribution function. So that's the cumulative probability of being any value from 0 up to and including little x. And then the order of the arguments is the same as for binom PDF. So for example, the probability of getting 3 or fewer heads when you toss 4 fair coins would be binom CDF of 4, 0.5, 3. All right. And to use the binomial distribution in R. So we're going to be working with many different probability distributions over the next couple of weeks. And all of them follow the same pattern in R. They have sort of a stem that tells which probability distribution we're working with. And then they have a prefix with one of these 4 letters. So the prefix D plus the stem binom gives the probability that y equals y. The prefix P gives the cumulative probability that y is less than or equal to y. Q is finding the value of y so that the probability that y is less than or equal to y equals q. And R generates random numbers from the binomial distribution. So for example, if we did D binom 3, 10, 0.4, that's finding the probability that y equals little y. So that's going to give the probability that y equals 3 when there are 10 trials and a probability of success equal to 0.4. Similarly, P binom is going to give the probability that y is less than or equal to 3. Again, when there are 10 trials and probability of success equal to 0.4. If we use R binom, that's going to generate random numbers. So here, I'm generating 1,000 random numbers from a binomial distribution with n equal to 10 and probability of success p equal to 0.4. So then, for example, we can look at the first 10 numbers in this vector x, and you can see they're all integers. They're all between 0 and 10. So that makes sense. These are all numbers of successes, say numbers of heads when we flip 10 biased coins. And And one thing that I often like to do is to make a histogram to represent the probability distribution. So we can do that using the hist function, H-I-S-T. So that gives us this distribution. And we can see this makes sense, that its peak is here near 4, and it has values between 0 and 10, with values that are low being slightly more likely than values that are close to 10, which makes sense because our success probability was less than 0.5. Questions about working with the binomial distribution in R or on your calculator? All right. And to show how Q-binome works, so if we use n equal to 10 and p equal to 0.4, here's a table of the probabilities that y equals little y for 0, 1, 2, up to 10. So we would generate these using d-binome. And then the second row is the probability that y is less than or equal to y. So these are the cumulative probabilities. So for example, the probability of being less than or equal to 0 is just the same as the probability of being equal to 0. But the probability of being less than or equal to 1 is the sum of 0.006 and 0.04. So we would find this second row using p-binome. So then, if we did, for example, Q-binome of 0.03, 10, 0.4, that's saying we want the probability to the left of x to be 0.03. And well, we can't get that exactly, but we do see that we can get 0.046 as the probability to the left if we pick 1. So that returns 1 because 0.046 is the next value that's just above 0.03. So we can get a probability of at least 0.03 by choosing a y value equal to 1. If we do Q-binome of 0.10, then that's going to look here. So if we chose 1, we couldn't get high enough. We couldn't get up as high as 0.1. But if we choose y equal to 2, then our probability is equal to or greater than 0.1. So that returns 2. So this is known as the quantile function. We're going to see more of it when we get into continuous random variables, but I just wanted to point it out so you're aware of it. All right. So let's suppose that 40% of UWEC students are in favor of making every Thursday Crazy Hat Day. You survey 5 different students at random. Try finding the probability that exactly 2 are in favor of Crazy Hat Day. So you can do this using the formula, using your calculator, or if you have a computer handy with R on it, then you can try using R as well. Pooja says, I got 0.3456. Do other people's work agree with that? Seeing some nods? All right. Yeah, so if we use the formula to do this, we have 5 choose 2 times 0.4 squared times 0.6 to the third. Excellent. Questions about this? All right. Now suppose that 40% of this class is in favor of Crazy Hat Day. There are 4 people in class in person today. There are 8 people registered for this class. And you survey 5 different students at random from this class. Would you find the probability in the same way? Let's see, thumbs up for yes, thumbs down for no.
I didn't see what the difference was with the last slide.
The last slide was 40% of all UWEC students. So thumbs up for yes, thumbs down for no. Yeah, thumbs down. So this is the situation we talked about at the start of class. We're sampling without replacement, and we're taking a sample that's large relative to the size of the population, because our population is only 8 people. So we can't assume independence. So in this case, we would want to use the hypergeometric distribution, which we'll talk about next week. And here's sort of a general guideline for what constitutes a large sample relative to the population. Is our sample size little n, so 5, is greater than, or I'd probably say, or equal to 5% of the population. So in that case, we don't want to assume independence, so we don't want to use the binomial distribution. All right. So this problem is not meant to have you do any calculations on paper, just think about it in your head. If you flip a fair coin 10 times, how many heads do you expect to get? 5. How'd you get that number? A half times 10. Yeah, so if y is a binomial random variable based on n trials and success probability p, our intuitive sense of how we compute the expected value of y is to take n times p. Let's go ahead and prove that this formula really works. So we're going to prove that if y squiggle binom np, this squiggle here means has the distribution. So it doesn't mean approximately, it means that y is a random variable with this distribution. Then we want to prove that the expected value of y equals n times p. So to start us off, let's start with the definition of expected value. So the definition of expected value is we're going to take the sum over all the values little y of y times the probability of y. So now let's make this specific to the binomial distribution. So for the binomial distribution, all the possible values little y are integers from 0 up to n. And we can fill in our formula for the probability that y equals little y. So now we know we're dealing with the binomial distribution. So our goal here is going to be to use algebra combined with facts about probability to try to rearrange this right-hand side to get it to look like n times p. And the first thing we can do is to notice that our first term, when y equals 0, the term is 0. We'd just be adding 0 times a probability. So we can remove that term. It doesn't add anything to our sum. So we can change that to a sum as y goes from 1 to n. And then let's go ahead and expand the n choose y. So we'll write that as a fraction using factorials. So take a moment to do that. All right, so that looks like that. And now let's further expand this y factorial in the denominator. So we know that y factorial is y times y minus 1 times y minus 2 times ... times 1. But let's just peel off the first factor of that. So we can write it as y times the quantity y minus 1 factorial. Anybody see how that helps us? Kyle.
The Y's cancel.
Now the y's cancel. And this is why we bothered to do that change of our summation to do y from 1 to n instead of 0 to n, so that we could do that expansion and then the cancellation without worrying about a term where y was 0. All right, so now here comes a cool trick. Notice that this thing in the summation has the form of substance times p to the y times q to the n minus y. That's kind of like the probabilities from a binomial distribution. So let's see if we can make it look more like the probabilities from a binomial distribution. So we can do this by using a substitution of variables. So let's let m equal to n minus 1, and we'll let z equal to y minus 1. And we want to rewrite our summation here to try to replace the n's and the y's with m's and z's. So first, we'll start by expanding this n factorial into n times n minus 1 factorial. Because that'll let us replace the n minus 1 factorial with an m factorial. And we can replace the y minus 1 factorial from the denominator by z factorial. And then I've also rewritten the p to the y as p to the z plus 1. All right. So now we have these two factors that have an n minus y in them. We have an n minus y factorial in the denominator, and we have a q to the n minus y. Notice that n minus y equals m plus 1 minus the quantity z plus 1. So if we distribute the minus sign to the z and to the 1, we get m plus 1 minus z minus 1. So that's just the same as m minus z. All right. So let's replace the n minus y's by m minus z. So that looks like this. We have the expected value of y is the sum as y goes from 1 to n of n times m factorial divided by quantity m minus z factorial times z factorial times p to the z plus 1 times q to the m minus z. All right. We can replace the n in our summation by m plus 1. And then if z is y minus 1, then as y is going from 1 up to m plus 1, z is going to be going from 0 up to m. So because z is y minus 1, we've subtracted 1 from both the lower and the upper bounds of our summation. All right. So now we just have an n left in our numerator, and we have this p to the z plus 1. Let's expand the p to the z plus 1 into p times p to the z. And then the n and the p don't depend on z. They don't depend on this thing that we're iterating over in the summation. So we can factor those out of the summation. So that becomes n times p times the summation as z goes from 0 to m of m factorial over m minus z factorial times z factorial times p to the z times q to the m minus z. All right, we're so close. Remember that the whole point of doing this business with the m's and the z's was that we were trying to make this stuff inside the summation look more like the probabilities from a binomial distribution. And we've done that. This is now exactly the formula to find the probability that z equals little z out of m trials and success probability p. How does that help us? Kyle.
Well, since z equals 0, we stated that with the first one, we had it the same exact way. When it was 0, everything was equal to 0.
We could do that, but it's actually helpful to us in a more direct way than that. We're taking the sum as z goes from 0 up to m. And if z is the number of yeses out of m trials, then those are all the possible values of z. So what we're doing here is taking probabilities and adding them up over all the possible values of the random variable. So that's equal to 1. So that means that our expected value of y equals n times p times 1. So we've proved the formula for the expected value that we conjectured based on our intuition about flipping coins. Questions about this? All right, so I have a summary of what we just did, but given the time, I think we will save that for our first start of class on Thursday, so after the exam. So please work on practice problems over the weekend, and I will see you on Monday for our review session.